Hello everyone, we are the team AMA and today we are excited to present our AgriBot, your smart farming partner for quicker, sharper and greener decisions. This system leverages AI-driven advisory solutions to transform agriculture into a more data-driven and sustainable farmer-friendly practice. Now, at AgriBot, our mission is clear and it is to empower every stakeholder in agriculture with human aligned and AI driven decision support. Our core values are accessibility, trust, and innovation. We want to ensure that guidance is not only reliable and accurate but also inclusive so that farmers also benefit equally across diverse communities. So these were our missions and values. Now, over to the description of our problem statement, which was a part of the hackathon from Capital One. So the problem statement is like in everyday life, farmers face critical questions every day, which are when should I irrigate to maximize the yield? Which seeds are best for unpredictable weather? Should I sell my produce now or wait? Where can I access affordable credit or government schemes, etc.? So currently these questions are answered through experience, guesswork or delayed advice, which is not always reliable. So our main task for this problem statement is to design a smart AI-driven decision support system that integrates multiple datasets and real-time data sources to give farmers clear, personalized and timely recommendations. Now, for this problem statement, our device solution is this. Firstly, the scope of our solution is currently limited given the limited time and efforts of the final submission. So, currently, we have five key districts of Uttar Pradesh: Kanpur, Lucknow, Agra, and Kannauj, covering six major crops like wheat, maize, paddy, tomato, potato, and sugarcane. We integrate weather data, soil health, mandi prices, and government policies into one unified systems. Predictive models help us forecast irrigation needs, crop yield, and price trends. So, for farmers, this means better decision making, reduced crop losses, and improved access to markets and policies. Now, moving over to the database schema which we majorly used five key districts of Uttar Pradesh as specified before, which were Kanpur, Lucknow, Unnao, Agra, and Kannauj. They were chosen because they are agriculturally significant and diverse in crop production. Among these districts, each district had 3 to 4 mandi markets, and each district is connected to multiple mandis, ensuring realistic price variations and local market diversity. As told before, we covered six crops and which were a mix of cereals and perishable crops representing both food security and cash crops. Now, these were the major five datasets which we used. First was the Mandi Prices database, which was downloaded from the official data.gov.in site. This database includes fields like state, district, market, commodity, variety, date, and minimum, maximum, and model price of the crops. This database enables to analyze price trends, mandi comparisons, and real-time lookup for the crop prices. The second database is soil health database, which contains nutrient profiles for soils in the same five districts, supports fertilizers recommendations and crop suitability advice, helps optimize yield while maintaining soil balance. The third database we used was irrigation knowledge base, which was scraped from United Nations Health and Crops website. This knowledge base contains crop wise irrigation guidelines: when, how, often, methods, and precautions, and it is linked to growth cycles of each crop. Now, this knowledge base provides farmers with actionable water management strategies also. The fourth database that we used were policies and schemes of the Government of India. We scraped all these policies and schemes PDF datas from the official data.gov.in website. So these PDFs contain collection of government PDFs on schemes, subsidies, and credit support. All this data is processed and indexed using vector embeddings for quick retrieval, and it helps farmers discover relevant policies instantly. Now, the last dataset that we used was the weather data API. It's not a particularly a dataset, but we use the weather data API for real-time and forecast of temperature, rainfall, humidity, and wind, which is necessary in crop yield and growth. This was sourced via Open Meteo API for district level accuracy, and it enables risk alerts, crop planning, and irrigation scheduling. Now, moving over to our system architecture. So, AgriBot system architecture is modular and robust. The first, whenever someone inputs a query, the end user sees the user interface, a Streamlit web app, and CLI supporting English and Hindi queries. Next, after entering the query goes to the NLP pipeline, which detects the language, classifies the intent of the query, and extracts entities like crop and location. Next, the extraction from the NLP pipeline goes to the core services of the AgriBot, which are the price queries through LLM and SQL are processed, weather insights from the Open Meteo come, and policy search using the FAIRS database. Now, next comes the data layer. For this data layer, the SQLite, FAS, and all the CSVs all interact among themselves with external APIs like Grok and Hugging Face. After this, this pipeline ensures that a farmer's query is processed, routed, and answered with farmer-friendly local advice. After this, we move on to the query workflow. A typical farmer query flows through multiple stages. Entry through the UI with auto detection of city and crop. Then comes an auto setup fallback. If the setup needed, it auto extracts city crop from the query and reprocesses it. Then comes the NLP pipeline, where the language of query is detected, the embeddings are normalized, the intent of query is classified, and the final entity is extracted. Then comes the routing stage, where the query is classified into whether policy, price, agriculture, or technical, or a general query. And after that, it is sent to the handler in agricultural advisor bot. This is also a Python file where the query finally goes to synthesis, where the final answer of the query is synthesized. So after this, we come to the synthesis of the answer. So there are different handlers which fetch data as needed and call the Grok LLM for concise, farmer-friendly advice in auto, Hindi, or English. Finally, the answer of the query is displayed as a formatted response with the sources that are appended to the chat history and rendered in Streamlit. After this, we move on to the limitations of our project. Currently, we face certain limitations. The first is data coverage, limited to static datasets, and expansion to live APIs is needed. The next are weather insights. This is limited to city level data. Roadmap includes farm level accuracy and crop stage modeling only. The next is model dependency. Currently, our complete workflow is reliant on external Grok API. Long-term goal is to download or a hybrid or local model and deploy it for reliability and cost optimization. The last limitation is multilingual constraint. Currently, it supports only Hindi and English, which limits accessibility. The goal is to expand this coverage to 10 plus regional language dialects and voice and IVR channels also. So, according to these limitations, there are some future enhancements which we would like to propose. The first is expanded data coverage. As told earlier, we plan to integrate real-time APIs, market prices, soil, weather, satellites, and unify multiple public data sets for hyper-local insights. The next is advanced weather intelligence. So, for this, we will upgrade to farm level precision forecasts with crop stage modeling, pest risk alerts, and seasonal trend predictions. The next enhancement is hybrid or local model development. To reduce the dependency on external API LLMs, we can deploy a local model which will be more reliable and also save much cost. The next enhancement is multilingual plus multimodal support. We would like to expand to 10 plus regional languages and dialects and add voice or IVR access and explore image based query input. The next enhancement is farmer centric personalization. We would like to enable personalized recommendations based on crop type, farm size, soil health, and financial needs. And lastly, trust and explainability. We would like to incorporate explainable AI outputs, confidence scores, and source citations to improve the transparency and farmers' trust in AgriBot. With this, we would like to conclude our video for the problem statement of Capital One. We, the team members, me, Astitva Roy, presenting this presentation, and my teammates Aman Nigam and Manavjeet Singh, we worked together in this problem statement and devised our solution. Thank you very much.